Welcome to the deep dive. You send us your sources, and we extract the crucial knowledge for you. It's your shortcut to getting well-informed without feeling overwhelmed.
Think of us as your guides, really. Navigating through the information, pointing out, the important stuff, maybe some surprising things along the way.
And today, we're diving into something pretty fundamental in the digital world, SQL Structured Query Language.
Yep.
Our source is the Mastering SQL ebook by Rajamakam and Tony Muthu. One of you sent this in, and it looked like a great resource.
It is. And our mission today, it's more than just defining SQL. We want to really get a feel for why it's still so important.
Right.
We'll break down the core parts, from the basics right up to some pretty advanced uses, and hopefully uncover some interesting bits you might not expect.
Exactly. We've got this ebook as our guide, so we'll be pulling straight from that. If you've ever wondered how all that online data gets managed, or maybe you're looking to level up your tech skills, well, you're in the right place. Okay, let's jump in. What is SQL fundamentally, and why should you care?
Okay, well, think about just the sheer amount of data out there every day. It all needs organizing, right? Managing somehow.
Right.
That's where databases come in. Basically, organized collections of data, and they're managed by something called a DBMS, a database management system.
See?
SQL, that's the language.
Yeah.
It's the standard way we talk to these databases. It's like the key, really, that lets us get data out, put new data in, change things. It's the bridge.
The bridge between us and the data.
Okay.
And the ebook really emphasizes how widespread it is. Is it really used that much?
Oh, absolutely. It's practically everywhere. Think finance, tracking transactions, healthcare, patient records, e-commerce, managing all those products you see online, tech companies, web apps.
Wow.
Yeah, SQL is often working behind the scenes. A huge chunk of the world's data, probably, sits in databases managed by SQL. That's why you see such a constant demand for people with SQL skills across so many industries.
And the ebook calls it a foundational skill. Why foundational? What does that mean if you want to go deeper into data stuff?
Well, mastering SQL gives you this solid understanding of how data is put together, how it's handled, and that knowledge. It's super useful as you move into more complex areas like data analysis, data science, even designing databases.
I see.
It lets you get at the data efficiently, clean it up, prepare it, which is like the first crucial step in pretty much any data project. Plus, having that core skill often means, better career opportunities.
Better opportunities are always good. Now, the ebook talks about the relational database model.
Yeah.
What's the main idea there?
Okay, so the relational model. Think of organizing data into tables. A bit like spreadsheets, maybe.
Okay.
Each table holds info about one specific thing, like customers or orders or products. Tables have rows. Each row is one item, like one customer. And columns, those are the attributes, like customer name, address, etc. The relational part comes from how these tables can be linked. They have relationships based on data, usual columns, so you can pull related info together from data.
So it's not just one massive list. It's organized tables that connect.
Yeah.
And the ebook mentions some popular databases that use SQL. Any standouts?
Yeah, it lists a few big ones. MySQL is mentioned. It's open source, very popular for web apps, big community support.
Okay.
Then there's PostgreSQL, known for being really robust, lots of advanced features, often picked for reliability, complex stuff.
Right.
Microsoft SQL Server, that's a big enterprise player, especially if you're in the Microsoft world. Oracle Database is another giant, often used for, really large-scale critical business systems.
Heavy hitters.
Yeah. And then there's SQLite. It's different. It's lightweight, file-based. You often find it embedded inside mobile apps or smaller applications where you don't need a whole separate database server running.
So a whole range of tools for different jobs. And if you're wondering about careers, the ebook lists some roles where SQL is key.
Definitely. The demand is broad. Data analysts, they use SQL all the time, extracting data, cleaning it, analyzing it for business insights. Database administrators, DBAs, they manage the databases themselves, keep them running smoothly. Data scientists use SQL heavily too, especially for getting and prepping the data for their models.
Right.
Software developers often need SQL to build applications that store and retrieve data, and BI developers, business intelligence folks, they build reports and dashboards, and that relies heavily on SQL to get the data. So across the board, it's pretty fundamental.
Seems like a non-negotiable skill if you're serious about working with data. Okay, let's get into the basics. The ebook mentions case sensitivity or the lack of it for commands.
Right. Generally for the SQL keywords themselves, like select, from, where it doesn't matter if you type them in uppercase, lowercase, or mixed case, the database usually understands. But, and this is important, the ebook strongly recommends using uppercase for keywords. Select, from, Where? Why? Readability. It just makes your code so much easier to scan and understand, helps separate the commands from your table and column names.
Like highlighting the verbs?
Yeah.
Makes sense. But it also says table and column names might be different.
Exactly. While the SQL language keywords are often case insensitive, how the database treats the names you give things, your table names, your column names, well, that can vary. Some systems will treat employees and employees as totally different tables.
Oh.
So you really need to know the rules for the specific database system you're using. Otherwise, you can run into errors just because of capitalization.
Good tip, especially if you work with different databases. Now, the basic structure of a query, the ebook lays it out clearly. Walk us through the core parts.
Okay, the absolute basic structure you'll see everywhere is select column 1, column 2, from table name, where condition. Let's break that down. Select is where you list the columns you want to get back. You can list specific ones or use the asterisk, A, which is a shortcut for all columns.
Great. The star means everything.
Yep. From Faratum just tells the database which table to look in. Simple enough.
Okay.
And then where. This part's optional, but super useful. It lets you filter the rows, you set a condition, and only the rows that meet that condition are included in your results.
And the ebook had a simple example, right? Finding employees in sales.
Exactly. Let's say you have an employees table. It's got columns like name, department, salary. If you want just the names of people in the sales department, the query is select name from employees where department sales.
Okay.
It tells the database. Look in employees, find rows where department is sales, and give me back just the name for those rows.
Clear and concise. Now, the ebook categorizes SQL commands. That seems helpful for organizing things mentally. What are the main groups?
Yeah, it uses 4 main categories, which is a pretty standard way to think about them. First up is DDL data definition. These commands define or change the structure, the schema of your database. Think create table to make a new table, alter table to modify one, drop table to delete one. Truncate also fits here. It empties a table but keeps the structure. So DDL affects the blueprint of the database.
Okay, DDL for structure. What's next?
Next is DML data manipulation link. This is about working with the actual data inside the tables.
Manipulation.
Right. The big 4 DML commands are select, getting data out, insert, adding new rows, update, changing existing data, and delete, removing rows. So DML is focused on the content, not the structure.
Got it. Structure is DDL, content is DML. What else?
Third is DCL data control language. This is all about security and permissions.
Control.
Yep. Grant gives users permissions like letting them read a table or update data. Revoke takes those permissions away. So DCL is how you manage who can do what. Crucial for security.
Okay. Security. And the last one.
That's TCL transaction control link. Commands like commit, rollback, save point, these manage transactions.
Transaction.
Yeah, a transaction is like a sequence of operations that need to be treated as one single. Either they all succeed or none of them. TCL ensures that happens reliably, keeps your data consistent, especially if multiple changes need to happen together.
Okay. Structure, content, security, and making sure operations are reliable. That framework helps. Now, the ebook dives deeper into those 4 main DML commands, starting with select again.
Yeah.
What else is key besides picking columns and filtering?
Well, besides just naming columns or using the for all columns, the ebook highlights the order by clause. Very important.
Order by for sorting.
Exactly. It lets you sort your results based on the values in 1 or more columns. You can sort ascending ASC, which is usually the default, or descending DESC. Super useful for making sense of the data when you get it back.
Right, presenting it clearly. What about adding new data with insert?
For insert, the ebook explains you name the table. Then you can either list the specific columns you're providing data for, followed by values and the data. Or if you're giving a value for every column in the table's default order, you can skip listing the columns and just use values with the data. A key thing it shows is inserting multiple rows at once. You just provide multiple sets of values in the values clause, separated by commas, much faster than doing one insert per row.
Good tip for adding lots of data. And modifying data with update.
Update uses the set clause. That's where you say which columns to change and what the new value should be.
Okay.
But the ebook gives a huge warning here. Always, always use a where clause with update, unless you genuinely want to change every single row in the table.
Dangerous otherwise.
Very. Forget the where clause and you could accidentally update your entire table. Big mistake potential there.
Definitely want to avoid that. And the last of the 4, delete, removing rows.
Yep. Delete removes entire rows. And just like update, the ebook stresses. Use a where clause.
Same reason.
Exactly. If you just write delete from table name without a where, you'll wipe out all the data in the table. Gone. So you need that where clause to specify exactly which rows you intend to remove. Precise.
Sound advice. Avoid accidental data deletion. Now, the ebook moves to SQL data types. This defines what kind of info goes in each column, right?
Precisely. Data types set the rules for each column. The book covers the basics. Integer for whole numbers, varchar for text strings up to noun characters long.
Variable characters.
Text T for longer blocks of text, date for dates, usually in YMMDD format, and decimal PS for numbers where you need exact precision, like money. Take P is the total digits, S is digits after the decimal.
And it shows an example, create table using these.
Yeah, a practical employees table. It defines an end column as integer and also the primary key. We'll get to soon. A name column is varchar 100, department is varchar 50. This salary is decimal 10, 2, good for currency, and hire date as date. It clearly shows how you define the structure and the type for each of information when you first create the table.
Helpful to see it laid out. Now, what if you need to change a table after it's created? The ebook brings in alter table.
Alter table is your go-to for that. Modifying an existing table's structure. The book shows examples like adding a new column, maybe a phone number column using varchar 15,
right.
Or changing an existing one. Maybe you need to make the name column longer or adjust the precision of the salary column. Alter table handles those kinds of structural changes.
Essential for adapting. What about getting rid of a whole table? That's drop table, right?
Of course. Drop table removes the table entirely. Structure, data, everything, gone.
Permanently.
Yes. The ebook rightly warns this is irreversible. Once you drop it, that data is effectively gone. So be absolutely sure before you use drop table.
Point of no return. It also mentions truncate table. How's that different from drop or even delete without a where?
Good question. Truncate table removes all the rows from a table, like delete without a where. But unlike drop, it leaves the table structure intact. The empty table is still there, ready for new data.
Oh.
The book points out truncate is often faster than delete for clearing out large tables because it doesn't log each individual row deletion. Big difference, though. Truncate usually can't be undone within a transaction, whereas delete often can be rolled back.
So truncate is like a fast, irreversible emptying, while drop is throwing the whole container away. Now, to make sure the data in the tables is good quality, the ebook talks about SQL constraints. What are those?
Constraints are basically rules you put on your table columns to enforce data integrity. They help make sure the data is accurate, consistent, reliable, prevents bad data from getting in.
Okay, like rules for the data. The first one mentioned is primary key.
Yes. A primary key constraint uniquely identifies each row in every table should ideally have one. The columns in the primary key can't have duplicate values, and they can't be NOL, empty. The ebook's employees example probably shows setting the id column as a primary key, ensures every employee has a unique ID.
Unique identifier, makes sense. And foreign key, that's about linking tables.
Exactly. A foreign key creates a link between two tables. It enforces referential integrity. It means the values in the foreign key column of one table must match values in the primary key column of another.
Can you give an example?
Sure. In our employees table, we might have a departmented column. That could be a foreign key pointing to the departmented primary key in a separate department. This ensures an employee can only be assigned to a department that actually exists in the department. Keeps the relationship valid.
It keeps the link solid. What about not NOL? Seems simple.
It is pretty straightforward. Not NOL just means a specific column cannot contain an NOL value. You must provide a value for that column when inserting or updating a row. The example might be making the employee name column not NOL. Every employee needs.
Makes sense. And unique. Similar to primary key, but slightly different.
Yeah, unique also ensures all values in a column are distinct, no duplicates. But unlike a primary key, a table can have multiple unique constraints. And a unique constraint usually allows one NOL value, since NOL isn't considered equal to not even another NOL. An email address column is a classic example for a unique.
Okay, unique but allows one null. What's the default constraint?
Default lets you set a default value for a column. If you insert a new row and don't specify a value for that column, the database automatically uses the default value you set. The ebook might show setting a default status, like active for new employees, or maybe a default salary.
Handy for columns that often have the same starting value. And the last one here is check. What is that check?
The check constraint lets you define a specific condition that values in a column must meet. For example, you could put a check constraint on the salary column to ensure the value is always greater than check salaries. Prevents negative or zero salaries from being.
So constraints are like the guardrails for your data, keeping it accurate and consistent. The ebook then suggests some practical exercises, like creating a products table.
Absolutely. Hands-on practices, creating tables, inserting data, using those commands. That's how you really make the concept.
Right. Okay, we've got the fundamentals down. Let's move up a level to intermediate SQL. A big one here is joins. essential for relational databases, yeah.
Oh, absolutely crucial. Joins are how you combine data from multiple tables based on related columns. See, in well-designed databases, you often split related information across different tables to avoid repeating data that's normalization. Joins are the way you bring that separated data back together when you need to query it. The ebook uses that employees and departments table example linked by department to show why you need joins.
And there are different types of joins, not just one. The ebook lists several.
That's right. Different joins give you different results depending on what you need. The most common one is inner join.
Inner join.
This one only returns rows where there's a match in the joining columns in both. If an employee has a departmented that doesn't exist in the departments table, that employee won't show up in an inner join result. It's about the intersection, the matching data only.
Okay, only the matches. What about left join?
A left join, or left outer join, returns all rows from the left table, the first one, and the matching rows from the right table.
All from the left.
Yes. And if a row on the left doesn't have a match on the right, you still get the left row, but the columns from the right table will just have NL values for that row. Useful if you want, say, all employees, even those not yet assigned to it.
Yeah.
You'd see the employee info and NL for the department name.
I see. So you get everything from the left plus any matches from the right. What about right join then?
Right join or right outer join is basically the opposite. It returns all rows from the right table, the second one listed, and the matching rows from the left.
All from the right this time.
Exactly. If a row on the right has no match on the left, you still get the right row with NLs for the left table's column. So if you wanted to see all departments, even those with no employees currently, you'd use a right join, you'd see the department name, and NL for employee details if the department is empty.
Okay, left gets all, left's right gets all right. And full join. Sounds like it combines both.
Pretty much. A full join or full outer join tries to give you everything. It returns all rows when there's a match in either the left or the right table. If a row from one table doesn't have a match in the other, it still shows up, with NLs in the columns from the table where the match is in.
So all employees in all departments, potentially with NLs.
Ideally, yes. But it's worth noting, as the ebook probably does, not all database systems actually support full outer join directly. You might need to simulate it sometimes.
Okay. And the last one mentioned cross. That one sounds a bit wild.
It can be. A cross-join creates what's called a Cartesian product. It matches every single row from the first table with every single row from the second.
Every combination.
Every possible combination. If table A has 10 rows and table B has 5 rows, the cross-join gives you 10, 5 equals 50 rows. It's not used very often because the results can be huge and often don't make logical sense unless you have a very specific reason for needing all pairing. The ebook's example probably pairs every employee with every department, which illustrates how big the output can get.
Okay, so joins let us weave data together. Next, intermediate topic. SQL aggregations and grouping. This is about summarizing data, right?
Exactly. Aggregate functions take a bunch of rows and perform a calculation to return a single summary value. The ebook covers the main ones. COUNT to count the number of rows, SUM to add up values in a column, AVG for the average, MIN for the smallest value, and max for the largest.
Useful summaries. But what if you want those summaries broken down, like average salary per department? That's where Group P by Y comes in.
You got it. Group P by is used to group rows that have the same value in one or more columns, and you almost always use it with aggregate functions. So for average salary per department, you'd select the department name and AVG salary, and then you'd add group by department name. This tells the database. Calculate the average salary, but do it separately for each unique department name. The ebook likely shows an example joining employees and departments first, then group.
So group by creates the categories for the summaries. Now, what about having? The ebook mentions it filters after grouping. How's that different from where?
That's a key distinction. Where filters individual rows before any grouping happens. Having filters the groups themselves after the aggregate functions have been calculated using group by.
Order matters.
Totally. So if you wanted to find only those departments where the average salary is over, say, $60,000, you'd first group by department and calculate AVG salary. Then you'd use having AVG salary $60,000 to keep only the group's departments that meet that condition. You can't use where for that because where doesn't know about the result of AVG salary.
Okay, that clarifies it. Where filters rows first, group by wise groups. Having filters the groups based on the aggregate results.
Got it. Next up, Subqueries and nested. Sounds like queries inside.
That's exactly what they are. A subquery or inner query or nested query, same idea, is just a select query embedded inside another main SQL query, the outer query.
Why do that?
Well, they let you tackle more complex problems. You can use the result of the inner query to help the outer query. Maybe the inner query finds a list of IDs, and the outer query uses that list in its where clause. It can break down complex logic into smaller, maybe more readable.
The ebook says you can put them in different places, like select or where.
Yeah, common spots are in the select list. Maybe to calculate a value based on another table. Very often in the where clause to filter the main query based on results from the subquery. And sometimes even in the from clause, the subquery runs first, and its result acts like a temporary table that the outer query then selects from, called the derived tables.
And there's a difference between correlator and non-correlated. Yes, a non-correlated subquery is independent. It can run all by itself. Its result is calculated once, and then the outer query uses that result. Think. Find employees earning more than the overall average salary. The subquery just finds the average salary once.
Okay.
A correlated subquery, though, depends on the outer query. It often references a column from the row currently being processed by the outer query, so it potentially has to run again for each row of the outer query. Think. Find employees earning more than the average salary of their own department. The subquery needs to know the current employee's department to calculate the right average.
So it's linked back.
Okay.
And nested queries are just more levels.
Yep. A subquery inside another subquery allows for even more intricate filtering or calculations, building up the logic step by step. The ebook's example of finding departments with employees earning above the overall average probably uses nesting.
Sounds powerful, but maybe slow? The ebook mentions performance.
That's a really important point. Subqueries, especially correlated ones that run repeatedly, can definitely impact performance. The database has to do.
So what can you do?
Often, you can rewrite a query that uses a subquery to use a join instead. Joins can sometimes be optimized better by the database. The ebook likely suggests considering joins as an alternative, especially for correlated subqueries. It might also mention things like using exists instead of in for certain checks, which can sometimes be more efficient. It's about knowing the options and understanding how the database might execute things.
Good to know there are alternatives for efficiency. Let's shift to set operations. Union, union all, intersect, except. What do these do?
Set operations combine the results of two or more separate select statements into a single result set. Think set theory from math union, intersection, difference.
Okay. Are there rules for using them?
Yeah, generally the select statements being combined need to have the same number of columns, and the data types in corresponding columns should be compatible. Also, the order of rows in the final result isn't guaranteed unless you add an order by at the very end. And crucially, they handle duplicate rows differently.
Let's start with union. How does it handle duplicates?
Union combines the results but automatically removes duplicate rows. If the exact same row appears in the results of multiple select statements you're unioning, it will only show up once in the final output. The ebook might use an example like getting a single list of unique customer IDs from two different tables.
Okay, union removes duplicates, so union all.
Union all keeps them. It just stacks the results of the select statements together, including any and all duplicate rows. If a row appears 5 times across the combined results, it'll appear 5 times in the union all output. Because it skips the duplicate checking step, union all is usually faster.
Faster, but includes duplicate. What about intersect? Sounds like finding the overlap.
That's exactly it. Intersect returns only the rows that are present in the result sets of all the select statements combined. It finds the common rows, maybe finding products that are in both the new arrivals category and the on sale category. One thing the ebook probably notes is that not all database systems directly support intersect. MySQL, for example, doesn't have a specific intersect keyword, though you can usually achieve the same result using joins or other methods.
Compatibility matters. And the last one, except or minus.
Except or minus in some systems like Oracle, returns rows that are in the result of the first select statement, but not in the result of the second select. It's like finding the difference.
Example.
Maybe find all customers who have registered but haven't placed an order yet. You'd select all registered customers, then select all customers who have placed orders, like union, except usually removes duplicates from its final result. And again, like intersect, direct support varies. MySQL doesn't have except, but you can simulate it.
Okay, so set operations give you tools to combine results in different ways. The last intermediate topic is window functions. Interesting name. What's special about them?
Window functions are really cool and powerful. They perform calculations across a set of rows related to the current row, similar to aggregate functions. But here's the key difference. They don't collapse the rows into a single output row.
They keep the rows.
Yes. They return a value for each row, calculated based on a window of related rows. This makes them amazing for things like running totals, moving averages, ranking items within groups like top 3 sellers per region, or even looking at the previous or next row's value without complex self-joins.
The ebook mentions partition by, order by, and over. How do those fit in?
Those are the core components. The over clause is what signals you're using a window function. It defines the window. Inside over, you use partition by to divide your rows into groups. Partition. The window function then operates independently within each partition.
Like group by, but doesn't collapse rows.
Exactly. And you use order by inside over to specify the order of rows within each partition. This is crucial for functions that depend on sequence, like running totals or ranking.
And the ebook lists some common window functions, like ranking.
Yeah, for ranking, there's row number, gives a unique number to each row in order. Rank gives ranks but skips numbers if there are ties. And dense rank gives ranks but doesn't skip numbers for ties.
Okay.
Aggregate functions like sum, avg, count can also be used as window function. With order by in the over clause, sem can calculate a running total, for instance. There are also functions like lag to get a value from the previous row and led to get a value from the next row within.
The ebook had an example, running total of sales by region. How would that work?
You'd use sum, sales amount, as the function. In the over clause, you'd partition by region, so the total resets for, and order by sale date to calculate the total in chronological order within the region. The result would give you each individual sale row plus a new column showing the cumulative sales total up to that point for that specific region. Super useful for analysis without losing.
Wow, okay. Window functions sound incredibly useful for analysis. Right, let's move into the advanced SQL section. First up, common table expressions, CTEs. I've seen those with clauses. What are they for?
CTEs are a fantastic way to make complex queries more readable and manageable. Think of them as creating temporary named result sets that exist only for the duration of a single query.
Temporary views within a query.
Exactly. You define them using the with keyword at the start. You give your temporary result set a name, define it with a select statement, and then you can refer to that name later in your main query, or even in subsequent CTEs within the same with clause. It helps break down complex logic into named logical steps. Much easier to read and debug than deeply nested subqueries sometimes.
And the ebook mentions simple and recursive CTs.
Right. A simple CTE is mostly for organization and readability, breaking down steps as we discussed. Like maybe one CTE calculates average salaries per department, and the main query then selects departments from that CTE where the average is above a certain threshold.
Okay, and recursive.
Recursive CTEs are specifically designed for querying hierarchical data. Think org charts, family trees, bill of materials. They have a special structure with an anchor part, the starting point, and a recursive part that refers back to the CTE itself to traverse the hierarchy level by level. Very powerful for navigating those kinds of structures.
So CTEs help organize complexity, and recursive ones tackle hierarchies.
Okay.
Next, indexes and performance optimization. We touched on indexes briefly, but let's dive deeper. How do they speed things up?
Indexes are like the index in the back of a book, but for database tables. They're separate data structures that the database can use to find specific rows much faster without having to scan the entire table page by page.
Big performance boost for select queries then.
Huge, especially on large tables. The ebook likely distinguishes between clustered indexes, which actually define the physical storage order of the data in the table, usually only have one, and non-clustered indexes, which are separate structures containing the indexed values and pointers back to the actual data rows.
And creating them is straightforward.
The basic syntax is pretty simple. Create index, index name on table name, column name. You pick a name, specify the table, and list the column you want to index.
Sounds great, but are there downsides? Any trade-offs?
There are. While indexes speed up reads, select, they can slow down writes, insert, update, delete a bit.
Why?
Because when you change the data, the database also has to update the indexes associated with that. That takes extra work. Indexes also take up extra storage space. So it's a balance. You index columns frequently used in where clauses or join conditions, but you don't necessarily want to index everything.
Makes sense. Balance reads and writes. Now, the ebook talks about transactions and concurrency right after indexes. We mentioned ACID before, but why is managing concurrent access so important?
It's critical because in most real-world systems, you have multiple users or applications trying to read and write data at the same time.
Correct.
Concurrency.
Right.
If you don't manage that carefully, things can go wrong. Transactions, adhering to those ACID properties, atomicity, consistency, isolation, durability. Ensure that database operations happen reliably as single unit. But when multiple transactions run concurrently, they can interfere with each other if not properly isolated.
Interfere how?
The ebook probably lists issues like dirty reads, reading data another transaction, non-repeatable reads, reading the same row twice in a transaction and getting different data because another transaction changed it, phantom reads, seeing new rows appear in a query result within a transaction because another transaction inserted them.
Yikes. How do databases prevent that?
Through isolation levels. SQL defines different levels that control how much one transaction is isolated from others. They range from low isolation, more concurrency, but higher risk of those issues, to high isolation, like serializable, which makes transactions behave as if they ran one after another but can reduce concurrency. You often manage this with commit to save changes and rollback to undo them if something goes wrong within a transaction. Understanding transactions in isolation is fundamental for data and
Definitely sounds crucial for reliable application. Okay, moving on to views. The ebook calls them virtual tables. What does that mean practically?
a view is basically a saved select query that you give a name to. It looks and acts like a table when you query it, but it doesn't actually store data.
So the data comes from the underlying query.
Exactly. When you query the view, the database runs the stored select query behind the scenes and gives you the result. They're useful for several reasons.
Like what?
Simplifying complexity. You can hide complex joins or calculations behind a simple view name. Security is another big one. You can give users access to a view that only shows certain columns or rows, restricting access to the underlying base. Data abstraction, you can change the underlying table sometimes. And as long as the view's definition still works, applications using the view might not need to change. And reusability, define it once, use it many times.
And creating managing them is simple.
Pretty straightforward. Create view name as select to make one. Create or replace view to update it. Drop view name to remove it. The ebook might show creating a high salary employee view, for example.
Are there limitations? Can you update data through a view?
That's a key point. Not always. Simple views based on a single table are often updatable. You can insert, update, delete through them. But views involving joins, aggregate functions, group p by, etc. are often not updatable. They're read-only. And of course, views depend on the tables they query, change the underlying tables drastically, and the view might break.
Okay, great for simplifying reads, maybe less so for writes. Let's talk stored procedures and functions. Reusable code blocks stored in the database.
That's the idea. Both are precompiled blocks of SQL stored in the database that you can execute on demand. Big benefit. Performance, less network traffic, code is already compiled. Consistency, centralizes logic. Reusability, and security. Grant execute permission without granting table access.
What's the main difference between a procedure and a function?
A stored procedure is generally used to perform an action or series of actions. It can take input parameters, perform DML operations, insert, update, etc., and can return output values via parameters. A function, on the other hand, is primarily designed to perform a calculation and return a single value.
Single value.
Yeah. You typically use functions within SQL statements, like in the select list or where clause, similar to built-in functions like CWEM or ABG. Procedures you usually call or execute as standalone commands. The ebook likely has examples, maybe a procedure get employees by department and a function calculate annual salary.
Procedures for actions, functions for calculations returning one value.
Got it.
And triggers. A special kind of stored procedure?
Sort of. The key thing about triggers is they execute automatically. You don't call them directly.
Automatically when?
They fire in response to specific database events happening on a particular table, usually insert, update, or delete operations. You define whether the trigger runs before or after the event.
Why would you want code running automatically like that?
Lots of reasons. Auditing is a big one. Automatically logging changes made to sensitive data. Enforcing complex business rules that go beyond some constraints. Maintaining data consistency across related tables automatically. The ebook might show a trigger that logs old and new salary values to an audit log table whenever a row in the employees table is updated. You can use special OLD and NW keywords inside the trigger to access the data values before and after.
Automated reactions to data changes. Sounds powerful, but the ebook mentioned potential downsides.
Yeah, because they run automatically, sometimes complex trigger logic can make it hard to follow exactly what's happening. Debugging can be trickier. And if a trigger does a lot of work, it can impact the performance of the original insert, update, or delete operation. So use them thoughtfully. Don't over.
Good advice.
Okay.
Advanced topics covered. Let's move to specialized SQL topics. First, advanced data types. SQL isn't just numbers and text anymore.
Not at all. Modern SQL databases handle much more diverse data. JSON support is common now, storing and querying semi-structured JSON documents right within. Some support XML too, with functions for parsing and query.
What else?
Arrays. Some databases like PostgreSQL let you store lists of values in a column. Geospatial types, geography, geometry are huge for GIS applications. Points, lines, polygons, and spatial queries. BLOBs and CLOBs for large binary or character data like images or long documents, and even user-defined types, UDT systems, letting you create your own custom data type.
Wow, very flexible. Another specialized topic, full text search. Better than just like.
Much better for searching natural language text. Like does simple pattern matching. Full text search understands words, phrases, can do Boolean searches, AND or not be, and importantly, can rank results by relevance.
How does it work?
You typically create a special full text index on the text columns you want to search. Then you use specific functions like match.against in MySQL or contains in SQL Server to run the search. The ebook likely shows examples of setting up the index and running queries, including Boolean operators and getting relevance score. It's designed for efficiently searching large amounts of text content.
Essential for searching articles, product descriptions, etc. Okay, next. Partitioning and sharding. Bringing up huge data sets.
Exactly. Strategies for managing massive tables or databases. Partitioning means splitting a single large table into smaller pieces, partitions, based on some criteria, like date ranges or regions. All partitions usually live within the same database. It helps performance because queries might only need to scan relevant partitions, not the whole huge table. Easier maintenance, too.
So splitting one table internally. And sharding.
Sharding goes further. It splits the data across multiple independent databases, often on different servers. This is about horizontal scaling, distributing the load and data across many machines. Essential for truly enormous data sets or very high traffic loads where a single database just can't keep up. The ebook likely discusses different ways to partition: range, list, hash, and shard, horizontal, vertical directory. Both aim for better performance, scalability, and manageable scale.
Partitioning is chapters in one book. Sharding is multiple books.
Got it.
Last specialized topic, working with temporal data, time-related stuff.
Yep. Handling dates, times, timestamps. SQL has specific data types. Date, time, or timestamp, year. The ebook shows how to insert data into these.
And manipulating them.
Lots of functions for that. Extracting parts, year, month, day, hour. Doing date arithmetic. Adding, subtracting intervals, finding differences, getting the current date time, formatting dates for display, date format, and importantly, dealing with time zones, converting between them if needed. You use these functions in where clauses to filter by time ranges or in group by Y to aggregate data by time periods, like monthly sales, essential for anything involving scheduling, logging, history tracking, time series analysis.
Comprehensive tools for time. Okay, let's see SQL in action. How is it used with programming languages?
Well, applications need to talk to databases, so languages like Python, PHP, Java, etc. have libraries or connectors. Python has SQL3, my6ul.connector, others. PHP has MySQL PDO, Java uses JDBC.
And they let the code run SQL?
Exactly. The ebook likely shows example, connecting to the database, creating a cursor or statement object, executing SQL strings like insert or select, fetching the results back into the program's variables, and then closing the connection. It probably highlights best practices.
Like what?
Using prepared statements or parameterized queries, absolutely crucial to prevent SQL injection attacks. Using connection pooling for better performance, especially in web apps. Proper error handling. Using transactions for operations that need to be atomic.
Key for building secure and robust apps. Next application, SQL in the cloud. How does that change?
Cloud databases like AWS RDS, Google Cloud SQL, Azure SQL Database offer SQL databases as managed service. Big advantage: scalability, easy to resize, high availability, automatic failover, automated backups, security features, less operational overhead because the provider manages the infrastructure.
But you still use SQL.
Yeah, the core SQL language is the same. How you connect might differ, using Cloud Console, CLIs, SDKs. Performance tuning might involve cloud-specific tools. Cost management is different, pay-as-you-go models. Migration tools exist to move databases to the cloud. But fundamentally, you're still writing select, insert, update, delete. The cloud just provides the scalable, managed platform around it.
So SQL skills are totally transferable to the cloud. Now, the comparison, NoSQL versus SQL, a big topic.
Huge. The ebook likely contrasts SQL's strengths, structured data, schemas defined up front, ACID transactions for strong consistency, great for relational data with NoSQL strengths.
Which are?
NoSQL databases, like MongoDB, Cassandra, Redis, often have flexible schemas or no-fix schema, are designed for massive horizontal scalability and high performance, sometimes sacrificing immediate consistency, think base instead of ACID, and handle various data models well. Documents, key value, graph.
So different tools for different jobs.
Exactly. SQL excels where structure and consistency are apparent. Finance. NoSQL shines with huge volumes of unstructured or rapid data, real-time application, massive. The ebook probably has a comparison table and discusses when to choose which or even how to use both together in a hybrid approach.
Makes sense. Choose the right tool. To write good SQL, the ebook covers best practice. What are the highlights?
Lots of good advice. Proper indexing is key, as we discussed. Writing efficient queries. Select only the columns you avoid select casually. Use joins effectively. Analyze query plan. Use limit when appropriate. Choose the right data types. Use where clauses effectively. Normalize your database design, but be aware of potential performance impact. Write readable code formatting, comments, meaningful names. Use transactions for critical multi-step operations. Monitor performance. And crucially, security. Use prepared statements to prevent SQL injection. Regular backups.
Solid checklist for writing better SQL. The ebook then lists common SQL interview questions. What kind of things come up?
A real mix covering the fundamental. Basic definitions. What is SQL? Differences. SQL versus MyS, SQL versus NoSQL, command types, DDL, DML, DCL, core concepts, primary foreign keys, normalization, joins, types, differences, indexes, subquery, aggregates, group by, having, order by, views, stored procedures, triggers, handling nulls, union versus union all, ranking functions, maybe even explain, self-joins. It's a good way to test if someone really understands the core mechanics.
Good overview of what employers look. Okay, last big section, SQL in the AI era. How is AI changing the SQL?
It's fascinating. AI is starting to act like a co-pilot for SQL. One way is using tools like ChatGPT to generate SQL queries from natural language requests. Show me sales for last quarter could become a SQL query.
Making it more accessible.
Exactly. AI can also help debug SQL errors, suggest optimizations like adding indexes or rewriting queries, explain complex SQL concepts, even generate practice problems. The ebook likely gives examples of prompting AI effectively as tasks.
So AI as a helper. What about optimizing queries automatically?
That's another big area. AI analyzing query patterns, predicting performance, suggesting indexes or rewrites. Some databases are even moving towards autonomous features where AI helps manage tuning and maintenance automatically. Tools are emerging that use machine learning to optimize SQL.
Generating SQL from natural language directly.
Yeah, NLP models trying to understand a plain English question, map it to the database schema, and generate the correct SQL. Useful for BI dashboards or allowing non-technical users to explore data. Still challenging for complex queries, but improving rapidly.
What else?
Yeah.
Automated maintenance.
Yeah.
Data analysis.
Yes. AI helping with tasks like predictive maintenance for databases, optimizing resource allocation, detecting anomaly. AI assisting data analysis by finding patterns or insights in data that humans might miss. Even embedding AI models within SQL, you could run predictions directly. Data cleaning is also crucial data to AI models. And AI-powered learning tools are appearing to help people more effectively. Even AI suggesting database schema designs or optimizing indexes. It's really integrating across the board.
It sounds like AI is augmenting SQL, not replacing it, making developers and analysts. Okay, final thoughts from the ebook. The future of SQL. Still relevant.
Very much so. According to the ebook, SQL is adapting. It's being used on top of NoSQL. It's central to scalable cloud data. Its integration with AI is only growing deeper. AI-assisted optimization, natural language queries, ML. Distributed SQL databases are emerging for global scale while keeping the and SQL features are crucial for data privacy compliance, masking encryption.
So the role of the SQL developer evolves.
Right. Needing broader skills, cloud platforms, maybe some data engineering, understanding AML basics, data privacy concepts, but the core SQL skill remains central. The message seems to be, SQL isn't static. It's growing and evolving with the data landscape.
Definitely not a dying language. It's adapting and integrating. Wow, we really covered a lot of ground there, from the absolute basics to the cutting edge.
We did, from select right through to AI-powered optimization and cloud database, a huge topic.
And the big takeaway seems to be that SQL is still incredibly important. It's that foundation, that versatile tool that keeps adapting to whatever the data world throws at it.
Absolutely. It's not just about querying anymore. It's about managing, analyzing, securing, and integrating data in increasingly complex environments. Still a vital skill.
So for you listening, maybe think about this. Which part of SQL's expanding world, maybe the AI integration or the cloud aspects or even those advanced analytics with window functions, which part sparks your interest the most? Where might you want to dig deep?
That's a great question to ponder.
A huge thank you for sending in the Mastering SQL ebook. It was a fantastic guide for this exploration. And thank you for joining us on this deep dive.
We hope this gave you a solid overview and maybe some new perspectives on what SQL can.
We love doing these. If you've got a source, an article, a book, anything you think would make for a great deep dive, please send it our way. Until next time, keep exploring.